Hello? Is this on? Do you hear? I know I actually don't need a microphone for this room. However, this is being recorded, so I want to make sure. But thank you all for coming to the epidemiology seminar. I'm very pleased to introduce Dr. Brooke Anderson. She's an assistant professor of epidemiology and assistant professor in the Department of Environmental and Radiological Health Sciences at Colorado State University. She's going to be speaking today on health risks associated with climate-related exposures, and you students might be quite interested to hear that she's actually published a number of open source R software packages to facilitate environmental epidemiological research. So I think that there's a lot of neat access and knowledge there for a lot of research, not just what Brooke will be presenting today. But thank you very much for coming, and I'm looking forward to your talk.
It's really great to be here, everyone. Good to see you all. I have to apologize ahead of time. You know, we had a tough go of it with school illnesses this year. I've got a 9-year-old, and I think there's one last one making the round, so I'm a little green around the gills today, but I'll give it my best shot. Sorry if my energy's a little low, though. So today I'm going to talk to you some about looking at hurricanes and human health, specifically in the United States, and a big part of this is going to be how we measure exposure to the storm. So this is a project I've worked on with a number of people, including people in engineering and in atmospheric sciences and some other fields who have helped with this exposure measurement part, which I think is really interesting. So a lot of the talk is going to be about that, but we also have some preliminary results on the mortality part of this, the epidemiological part, and that analysis is led by my doctoral student, Mei-Lin Yan, so I'll recognize that again when I get to that part, but I'm excited to be able to show some of that as well. So this past year really raised the conscious level a lot for thinking about human health related to hurricanes. And normally I'm a pointer, so I'm probably going to try that some, but I'll try to use my pointer here so that people looking online can see that too. But these are some of the billion-dollar disasters from this past year. And 3 of those, which I think we all heard about that, were hurricanes. Hurricane Harvey, which hit Texas, Hurricane Irma in Florida, and then Hurricane Maria, of course, in Puerto Rico. And if you look online and do a Google search, there's a lot of information and studies, very interesting stuff out there about hurricane fatalities in the United States. These are just 3 of them. These are all national level studies that went through and looked at fatalities related to tropical storms. There are some key limitations in these types of studies, though. They have very good information for some purposes, but because of the way they're measuring fatalities, there's some key limitations as well. So let me talk a little bit about that. I realize this is small, so I'll help you read it. This is a death certificate, and I want to talk about how we pick out the fatalities related to a storm. So on a death certificate, you have room for the immediate cause of death and then things that led up to that. The immediate cause of death in this case was a crushed chest, and it said on this death certificate that it was from a shed collapsed during hurricane. These words are really key for people being able to go back and identify the fatalities that were linked to a hurricane for the types of studies that have been done so far. If this had not been included, this death might not have been linked through in those fatality totals. These can also pick up things that are non-accidental. In this case, the immediate cause was acute respiratory failure. Before that, that was related to severe emphysema. And even before that, related to heat and loss of air conditioning from a power outage during a hurricane. Again, you can see that in this case, the person who wrote the death certificate made the link that this was something related to the storm. And that's how it made it into the final fatality count. In doing these kinds of studies, these researchers have done their best to pick all those up, and in some cases have even gone back and tried to look at news reports and talk with family and do these other things to try to link specific deaths to the storm. But the problem is, if it's hard to tell if a specific death would not have happened without the storm, it's very hard to pick it up this way. This has really come up with Hurricane Maria this past fall. So this is actually something done by the New York Times. The official death, so this is when Hurricane Maria made landfall in Puerto Rico, and these numbers are for Puerto Rico. And you can see this red line along the bottom. This is kind of the accumulating official death toll from going through and linking specific deaths to the storm, saying this death would not have happened without the storm. At the time they did this, or the time they're stopping right here, this was up to about 60 deaths, I think 64 maybe. But they went back and looked and they said, what if we compare it to what happened the years before the storm? And this line up here is the growing number of excess deaths that are in excess of what happened during a similar period the previous years. And there you can see we've got a number of deaths potentially linked to this storm, an order of magnitude larger than the official death toll in that case. And a lot of these might be things that are pretty common causes of death, like cardiovascular and respiratory deaths, where it's not unexpected that it happens. So it's very hard to say that it wouldn't have happened without the storm, compared to something like a drowning or a death from carbon monoxide poisoning, where it's much clearer to make those links. This is looking at how the New York Times did that. You can see again, we have Hurricane Maria making landfall right here. And they took deaths from the previous 2 years. These are all kind of a running smooth of this, so they don't look too jagged. And here's the deaths after the storm, how they kind of went up and stayed up. We've seen some evidence from other specific storms that there might be key risk to some of these common causes of death or other common health outcomes. A lot of it comes from Sandy. Sandy came through in 2012. It hit a very highly populated area. And a lot of studies have come up that looked at the impacts of that on health. And they found things like a changing pattern in emergency department visits, increases in food and waterborne diseases, especially among the elderly, increased rates of myocardial infarctions and hospitalizations for dehydration, and also generally a difficulty in continuing your typical standard of care for chronic conditions, things like getting medicine, refilling prescriptions, getting dialysis for people who need it, things along those lines. So for this project, this is kind of a large project that's spanned a few years now and has quite a team on it. But our first project aim was to assess the exposure to tropical storms for all of the storms that came close or made landfall in the United States between 1988 and 2015. And I need to go back. We can rerun some of this for 2016 and 2017, and I need to add that. The next question was, there are all these different hazards of the storm. I'm going to talk more about that in just a second. But we wanted to look and see if we do county-level classifications of exposure to the storm, how well do those agree when we look at different hazards of the storm? So we did that for a large collection of storms for all of the eastern United States counties. And then finally, as I mentioned, we've gone through and we're using this now for epidemiological research, linking through to the risk for some broad-scale classifications of disease. So all-cause mortality, and then also all-cause, respiratory, cardiovascular, and accidental mortality. So I'm going to give some of the results we're getting on that. And then finally, and I think this is really important, I'm very big on open source software, making data available when possible. We can't share the health data that we have on this, but we can share the exposure data to make it easier for other people to work with us. So part of this was taking that large-scale exposure measurement at the county level and making sure it's openly available to anybody else who wants to use it to pair up with their own health data, for example, for epidemiological research. So I'm going to talk a little bit about how we did that, and we did that through some open source software where we not only put the data out there, but we also put tools for mapping and exploring and generating data sets with it. All right, so the first part I'm going to talk about is assessing this exposure in the first place. So hurricanes are kind of tricky. Before this, most of my work had been, some of it on air pollution, which is also pretty tricky in some cases, but a lot of it on heat waves. And for heat waves, we have pretty good measures of temperature. It's pretty steady across the community. And what we're measuring at the weather station is the exposure that we really care about. We think that it's the temperature itself that's causing this physical reaction, and that's what we're measuring. Hurricanes are this multi-hazard kind of thing. This is from the New York Times. This is showing some of the impacts of Harvey. You can see where it made landfall. There were very heavy winds. There was a lot of damage to structures themselves. In areas around that, there were also, because of not necessarily building damage, but because of damage to trees, there were lots and lots of power outages. Some of those lasted quite a while. You can get tornadoes from these systems, and those can cause damage even kind of far away from the initial track. And then, of course, what we heard most about from that storm was in Houston, the massive flooding. And this, as a side note, quick pop quiz, does anybody know the only tropical storm whose name was ever retired? Everybody knows for hurricanes, if it's particularly severe, they retire the name. Otherwise, they loop it through the next year so they don't run out. Katrina was a hurricane. Oh, yeah. So typically, it's really severe hurricanes. A lot of times, they're ones that are the category 3, 4, 5. No? Tropical Storm Allison came through, and it hit Houston and caused massive flooding. Not a lot of rain, but extraordinary flooding. It went up in the United States, came back, and hit it again, coming back through. And actually, a lot of their hospital and medical complex in downtown got flooded, and it caused huge problems. So you can have really severe impacts from different hazards, and some of the ways that we measure storms might not pick up some of the potential impacts. The impacts also don't stop when you get inland. This is from AccuWeather as Harvey went through. You can see that they're forecasting downpours for a lot of the inland part of the southeastern United States, flash flooding, and tornadoes again. So I haven't done much with causal inference, but I think it's a very interesting idea, and I particularly like the idea of counterfactuals. And I think with hurricanes, we've got a very clear picture of that kind of idea, because when you're a few days out from the storm, what they do to measure the storm is they have lots of different models. And these are all dynamic models that have physics in them that are trying to capture what might happen. And they'll plot what are called these spaghetti models or spaghetti plots, where each of these little lines shows what one model is saying they expect to happen here. This is for Sandy a few days out, and you can see some of these have it coming in and hitting New York, much like it did. Some of it have it going up and hitting Boston, and a lot of them have it going out to sea and not causing any impacts at all. So when you think about if a community was exposed to certain hazards of the storm, some of that depends on which direction the storm decides to take kind of early on. So if it had gone this way, we wouldn't have had exposures to all of those places. But if it comes in here, then all of a sudden we do have a lot of exposures, and they can be from a lot of different things. So if we try to map out this process, the tropical storm path is really kind of helping to determine what exposures we have in a certain area. And those exposures can come in the form of very severe winds, rainfall, flooding, tornadoes. And then also, kind of linked off to the side of this, distance from the storm track itself isn't going to cause any problems, but it might work as a surrogate measure for some of these other exposures, and it's much easier to measure than some of these others. And I'm mentioning this because actually quite a lot of studies have used this as a surrogate for general exposure to the tropical storm. This is one example. This was looking at fatalities, and here they took the fatalities that had been specifically linked to the storms, but they were trying to match it up with exposure to the storm. And for exposure, they took the storm's track. So this is an example. And then for counties that the storm went directly through, that was given a primary exposure to that storm. The ones touching those were secondary, and the ones touching that were tertiary. So a fair number of studies use this kind of distance from the storm track as a surrogate for being exposed to the storm. And their actual conclusions here, where they were linking up things that were specifically linked to the storm, they found, well, actually we're seeing, not too rare that there's a flooding death from inland flooding that's not in this exposed area, so maybe this isn't a great idea. Others do things that are a little bit more complex. This was a study in Florida in 2004, and there were several storms that came through there. You can see each of these is the track of a storm that came through, and then there was one that came up kind of through the panhandle. And they did a mix where it was either that the storm had come through that county, but then also if there were very high winds, even if it hadn't come directly through the county, that would get counted. And they also included some other pieces like evacuations to try to figure out which counties were exposed to the storm. So it's not a straightforward question, but the kind of the upshot of that is that it turns out people have measured this exposures to the storm in a lot of different ways for epidemiological studies. These are all different health-related studies. Over here, I've put the kind of general category, so a lot of stuff on birth outcomes and mental health, and then some on mortality and a few on other health pieces. If it has a colored square, it means that they use that metric, a metric based on distance in this case, to help measure exposure. And if they have multiple of these, it might mean either that they tried one and then they tried the other as a sensitivity analysis, or that they did something that combined the two. The other piece here, a lot of times we go into these and we don't know what cutoff is the right cutoff for being exposed to the storm. So if it's wind, how high the wind needs to be. If it's distance, how far from the track. So the ones that are darker tested several different thresholds on that to assign exposure. Damage here is often based on FEMA, and then the other can include things like evacuation orders and a number of other things. But you can see here that we've measured this a lot of different ways. That makes it really hard for us to get a consensus view of what we think the risks are, among other issues. So I think it would be very helpful to have some standard data where people can test the same kind of exposure metric that somebody else did, and hopefully, measuring exposure in a way that is thoughtful and useful. So in this first part, I'm going to talk about how we measured this, and we measured this for 5 different metrics: wind, rain, flooding, and tornadoes. Those are kind of the hazards. And then distance from the storm track, which again is not a hazard itself, but has been used as a surrogate. All right, so for distance from the storm track, we took what's called the best tracks data. This is kind of like the official version of where a storm went. The National Hurricane Center maintains this, and they do a very good job of going back and getting it in very good detail. And we went through, and for each county at the population mean center, we measured the distance from the storm track to that county center for every point along the track. This is an example for Floyd from 1999, which hit the area just south of where I grew up, so it's one I'm very sensitive to. And from this you can see then we could identify the point that was closest, and we took that distance as the closest distance that the storm ever got to that county. And this is a little bit simplistic. This is every 6 hours, which is how they measure this. We actually went back and interpolated this to every 15 minutes, so it was a little finer than this in practice, but the graph gets a little messy if I try to show that. All right, so on to the hazards. That, as I mentioned, was the easier one to measure. So for rain, again, I'm going to refer to temperature, for air pollution, for a lot of other things. We often will use stations, weather stations or air pollution monitors. It turns out in hurricanes, a lot of those fail. So a lot of times when the winds get really high, these get swept away, or the rain's blowing sideways, so it's not going in. We also wanted something that was spatially continuous and, as I mentioned, temporally continuous. No missing data, especially when we want it the most. So we worked with some folks at NASA, and we used something called NLDOS2. This is a reanalysis data set. Has anybody taken kind of a spatial or GIS, spatial statistics or GIS class? Did y'all talk about kriging, some of the interpolation methods? So this is like take that and go way further, because in this case, they have taken, it's being informed somewhat by those station measurements, the observed data at different points. But to interpolate across that, they're actually using these weather models that kind of like work in the physics of what they think is going on. So it's a way for them to aggregate all this type of data in a very thoughtful way and come up with a smooth, continuous surface of what they think is going on. So it's done in a gridded way where there are these regular gridded spots. And the folks from NASA took that and brought it to the county level, which is where we have our health data. And they've actually posted that as well on the CDC Wonder data set. Has anybody heard of that? It's a really great resource. and temperature data as well. So this is what we used, and we paired it up with storm track. So we didn't want rain that was very far away from the storm and unlikely related to the storm to be attributed to a storm. So we identified any rain that occurred within a certain distance from the storm, and we used a very wide distance that except for a few rare cases, seemed to pick up just about everything. For winds, we have the same problem. The way that we measure winds, those instruments tend to get blown away in the very worst storms. For the reanalysis data set, that has some winds, but for the rainfall, we want cumulative. So it's okay that we only have a daily measure or maybe some hourly measures of that. For wind, we want to get like a very precise measurement, and the time scale for a lot of the reanalysis data we have is just too coarse for that. So we went back and we worked with some atmospheric scientists and some engineers who do wind speed models for modeling, predicting power outages during storms. And we used that and characterized wind speeds, modeled wind speeds for all of these storms at the county level. And then for flood and tornado events, NOAA keeps a database of severe storm events. And so we went through, and again, we paired up, that's at the county level, and we paired those up with storm tracks and distance from the track and timing. And so we identified the events that had happened within a certain range of the storm track with the starting date for within a certain range of when the storm had come closest to that county. So several of these, distance, rain, and wind, we got at the continuous level, and the data that we share has that at the continuous level. But often for epidemiological studies, we use a kind of binary. It was exposed to the storm, it wasn't exposed. So for the things that I'm going to show in just a minute, we looked at those binary classifications and how well they agree across these different exposure measurements. And for those for distance, we used that the county population mean center was within 100 kilometers of the storm track. For rain, as I mentioned, we chopped out anything outside of 500 kilometers from the storm track because in almost every case, except for one storm in Texas, I think, there wasn't rain that far out that was still associated with the storm. And then we did the county had 75 millimeters or more of storm over a period from 2 days before the storm to a day after. For wind, we did that the model wind speed was 15 meters per second or higher. And then for floods and tornadoes, these are listed, as I mentioned, there's either an event listed there or there's not an event. So it's already kind of naturally binary. And we made this, again, this criteria that it had to have happened within 500 kilometers of the storm track. We're figuring things outside of that probably were not linked. And that's a pretty liberal range. Any questions so far about how we measured it?
Where's the county population mean center from? Is that census?
Census, U.S. Census.
Every year that comes out?
We got it from 2010.
Okay. So
Yeah.
the decennial.
Yeah. All right, so it turns out that if you look at these different metrics, they can be really, really different in which counties were exposed to which elements of the storm, which I think it has really interesting implications for thinking about this for health research. This is an example for Ivan. Ivan came through, it actually made 3 U.S. landfalls. It came through near the mouth of the Mississippi, back over the Atlantic, south, and then over around like southern Florida, and then back in between Texas and Louisiana. So if we look at the distance-based metric, you can see that that just follows the storm track. This is very similar to the plot that I showed before that was showing for that one that looked at flooding deaths and kind of did like the counties out. In this case, we're not counting counties out, we're doing a set distance. But we did it evenly on each side of the track, which is typical to how most of those are done. If you look at wind, on the other hand, I'll go over here, most of those exposures are very close to where it makes landfall. And they can spread out more than the distance-based metric might right near the coast, but these storms die down very quickly once they don't have water to feed them anymore. So as they go inland, the wind speeds die down very quickly. Some of the other forces do not. With the rain-based metric, there you can see that there was really extensive rain from this all the way up into Pennsylvania and up a little bit further into New England. A lot of times these storms will dump a lot more rain once they get inland. A lot of them make what's called an extratropical transition, as they're moving up. Sometimes they'll merge with another system. And a lot of times that doesn't mean a lot of wind, but it means loads and loads of rain. You'll see this pattern going through. This one kind of went to the left of the Appalachians, but a lot of times the Appalachians are a marker for where the rain happened. When the storm hits that system, it can kind of shear out lots of rain. So a lot of times you'll get a lot on one side and not as much on the other. And a lot of times this rainfall happens on the left side of the track as it goes inland. The flood-based metric in this case, you can see kind of follows similar patterns, although it's not exactly the same places. And then interestingly, the tornado metric is picking out some counties in some cases that none of the other metrics you had exposures for. And a lot of times tornadoes from the storm happen on the right side of the track as it goes inland. So you get kind of a very different pattern from that. So we wanted to look at this across lots of storms. The way we chose to measure this, if we just measured agreement, we might get like a very high value just because a lot of counties aren't exposed to a lot of storms. And so if you have agreement with the things that are both saying no, then yes, it agrees, but it's a little less helpful because often what we care about are the places that are exposed and what we're picking out. So instead we used a metric that's been used some in ecology, and I think like I can't remember the name of this, but the study of like citation counts and who cites who and some of the things like that. But it's often done when you have something that's rare and you're trying to measure co-occurrence of it. It's called the Jacquard Index. And what it does is it takes, if X1 is the set of counties that are exposed based on one metric, say distance, and X2 is based on another metric, say wind speed, the numerator is the number of counties that are assessed as exposed based on both of those. So here, it might be the counties very close to the storm and very close to the coast. The denominator is the number of counties exposed based on either of those. So in other words, this is the percent of counties that were exposed based on either metric that agree and were exposed based on both. I had to sneak a heat map in because I think like the people in genomics have too much fun with those. We better do some too. So this is a heat map. Here, each of the rows is showing a storm. The color shows the Jacquard Index. So in other words, up here, this is saying that for Irene, about 80% of the counties that were assessed based on either rain or wind agreed in that and were assessed based on both. Over here, this shows the total number of counties exposed, and I couldn't show all of the storms here, so I've only shown this for storms that had lots and lots of people, I think 250 or more, lots of counties, exposed based on at least one of the metrics. And then these are grouped so that they're similar patterns. So in other words, here, Floyd and Irene had a pretty similar pattern across this in terms of which of the metrics agreed well with each other and which didn't. So the first thing here, the tornado metric really does not agree well with anything else. So if you think that that is the pathway for causing health effects, then you really need to use that as its own metric. Anything else you try to do is not going to capture that particular exposure very well. As we go across, there's a range. So there are actually some storms where the agreement's not too bad. Floyd and Irene are two examples. Both of these came and kind of skimmed along the eastern seaboard, moving north. And so they stayed over the water, at least half of them, so they kind of kept feeding on that energy. And both of them caused lots of flooding. For Floyd, it was in North Carolina, and for Irene, it was further up in New England, Vermont, I believe. But for these, there's fairly decent agreement, somewhere 50% or more for everything that doesn't involve tornadoes. But for a lot of the storms, there's really not a lot of agreement across any of these. So these are cases, again, where the storm was exposing lots and lots of counties based on at least one metric. But there's not a lot of agreement if you look at one metric in terms of picking out the counties that were exposed based on another hazard. So when we look at this across a lot of storms, you can really see the implications that this might have when we want to go and look at human health impacts. So here I've gone through and I've taken, for the data that we had, I've calculated the number of hits per county per decade, kind of an average number. This is for the wind-based metric, and unsurprisingly, you can see this really clings close to the coast. So again, these storms, they become much less severe once they come inland in terms of the wind speeds. So really, there's nothing kind of, I think this is around 200 miles in. I could be wrong about that. But once you get past there's really very little in terms of exposure at the county level from any of these storms. On the other hand, if you look at rain, you can see that a lot of these exposures go well inland. And again, I mentioned the mountains. You can see that there's a big split when you get to the mountains where a lot of these come in. And actually, some very severe impacts have come in areas like Virginia, this part of Virginia, from Hurricane Camille, when it came in and dumped a lot of water and caused massive flash floods and landslides and things like that. I also wanted to talk about this in context with a real study. So this is a really interesting study that came out. It looked at West Nile after Hurricane Katrina. And they came through and they wanted to look at exposed counties and compare the West Nile after the storm compared to the rates of it that they were seeing before the storm. They used distance from the track and they used it evenly on either side. And they added, which was very smart, they added this restriction that they'd only look at the points where the central strength of the storm was 75 miles per hour or higher. Their hypothesis looks kind of like this. So Hurricane Katrina had really strong winds, caused a lot of damage to the homes, and because people were outside, for example, repairing the damage to the homes, they were exposed to more mosquitoes, and that is the pathway that led to this. So they really think this pathway is going through the winds and the damage to the homes. They didn't model the wind speed for the exposure, though. They used distance from the storm track as kind of this surrogate of that exposure. So we can look through and see if you take distance to the storm and then you take the sustained winds, you can see how this could be problematic, not necessarily for this study, but if you try to apply this to lots of studies or you don't do it in a way that is very thoughtful. So as the storm comes in, as I mentioned, the most severe winds are right when it makes landfall, and actually they extend much further to the right of the storm than they do to the left. It's very uneven, and that's because these storms are moving like this, and then they're moving forward this way. So on the right-hand side of the storm, you add those two together in terms of the wind speed, whereas on the left-hand side of the storm, the forward movement and the rotational movement offset each other a little bit in the wind speeds. So if we look at a binary exposure, and I picked here the wind speed threshold that gave the most similar look to these, you can see that using distance to the storm is missing some of the exposed counties to the right of the storm, and then also is missing an exposed county right here that was nearer to the landfall, but then has some extra counties over on the left-hand side. If they had not done that threshold of the 75 miles per hour, they would have had a much more severe problem of capturing a lot of the inland areas that weren't necessarily exposed to that hazard of the storm. All right, so I want to talk next a little bit about the results that we're getting on tropical storms and mortality risk. So we've taken this exposure data now and we're looking at it in the context of US cities. And part of the question here is that phenomenon that you saw in Hurricane Maria, where there were many more deaths if you compared to previous years than if you looked at the fatality toll. Is that something that we see in lots more storms, or is it something that's very specific to that storm or to just some very severe storms? So for this, we used an extended version of the NMAPS data set, which I think your new dean had a very big role, John Samet, in initially putting together. And it was used to study air pollution initially. It's also been used to study a lot of other things, temperature, heat waves, but I believe that this is the first case of using it to study the impacts of tropical storms. So we have a number of communities. Each of the circles shows a community. They're each one or more contiguous counties. We only looked at the ones on the eastern side of the United States because we're looking at Atlantic Basin storms. And for all of these, we have about 75 communities in total. And almost all of the ones short, maybe 10 of them, were exposed to at least one storm based on at least one metric. For each of these, we have a time series between 1987 and 2005. We only used 88 to 2005 because there's some concerns about some of the hurricane data before that. But for each of those, we've got a time series where for each day, we've got the daily number of total deaths in the community, the number of accidental deaths, respiratory deaths, and cardiovascular deaths. These are all of the storms that came either made landfall in the United States over this time period or came within a certain distance of it. So ones that came very close, kind of sideswiped. From this, we wanted to measure the relative risk of mortality, and we measured this conceptually as the rate of deaths during the storm compared to what we would have expected without the storm. So this is ecological data, right? We're kind of aggregating it up. And in this case, what I care about is actually the kind of the ecological level. What are the rates in the community compared to what we would have expected without that? A lot of times we care about the individual level, but in this case, I think if a storm, even if the person wasn't directly exposed to the wind or to the rain or to something like that, if the exposure of the community to the storm caused issues, which could have come through problems with medical delivery or transportation or even evacuations or things like that, I think it's really interesting to measure the consequences that that has across the community. And we measured this in two ways. First of all, just for the day when the storm came closest to that community, and then for a period from 2 days before to 7 days after the total storm period. Has anybody here done much with, I'm talking about, air pollution and temperature, done much with time series or case crossover or some of these types of studies for air pollution and health or for temperature and health? A little bit? Yeah. Okay. So this shares a characteristic with those. One of the key confounders that we have here is season. So if you look at the trends of mortality over time, there's a strong seasonal pattern where they're higher in the winter and then lower in the other times of the year. Hurricanes also follow a very strong seasonal pattern. So here I picked out 3 counties, Miami-Dade, Dare County, this is in the Outer Banks of North Carolina, and then Hancock, Mississippi, this is near the mouth of the Mississippi. And for each of these, the y-axis is showing the number of storms over our period that occurred in that month. So first of all, there are no storms outside of the June to November period in any of these communities. And even within that period, there's this very strong trend where there tend to be more of them in August and September. And, that's varying a little across the communities, but it still has a strong trend. So a way that a lot of time series and case crossover studies look at this is they will use for time series, they use a flexible control for long-term and seasonal trends. And then for case crossover, they're taking other days in that same month of that same year with the same day of the week, and those serve as the comparison. We were concerned about doing either of those, and that's because if we truly have this case where the death rate goes up and stays up for a period, both of those, in most cases, are using some of the period after the storm to help control for those long-term and seasonal trends. So we could underestimate the effects because we might pick up days in this period where things are still elevated, and we're using that as kind of like the comparison of what we would have expected if the storm hadn't have happened. So I was concerned about that. Some studies have gone through, including some studies of specific storms, and they've looked at the period right before, and they've said, okay, how does what happened here compare to what happened right before? And they're probably getting a pretty decent estimate, but there's a chance as we go through lots and lots of storms that's going to bias our estimate upwards, that we're going to overestimate. And that's because you can see here we're getting into kind of September and August. These are periods at the low point and then where you're starting kind of the upswing of that mortality trend without the storm. And so if you're always picking a comparison period that you would expect to be a little bit lower just because of those seasonal trends, and then comparing it to your storms, you have the potential for that. So where we have this fall pattern, that was a concern too. So what we did instead was we picked comparison days from the same city and the same time of the year, but other years. It makes it a little harder to control for long-term trends, and we had to put in a model control for the year. But we're hoping that that was a little bit more stable to some of these issues of causing such a big change and one that lasts that might cause some problems with making comparisons within the same year. So this is an example just of some of the more severe storms that we had the first year, in Miami-Dade over some of the years. Irene in 99, Katrina in 2005, and then Wilma in 2005. And this is kind of a cartoon version of what we did. So for each of the storms, we picked days that were around that same time of the year in other years. And instead of taking every other possible day, we wanted to make sure we were balanced across all the storms we looked at. And in some cases, we had storms that came very close together or were on the same day of the year in different years. And in those cases, we didn't pick a day that was very close to another storm as a potential control. And so we did just a sample of 10 rather than picking every single possible one we could do. And that ensured that balance across the different ones. So we did this, and then as I mentioned, we put in a model control for year, we put in a random intercept in the model for the community, and we put in an offset for the population of each community. And then we modeled the change in rates using an over-dispersed Poisson distribution. When we looked at this, and this is when we were measuring storms based on a pretty high wind speed threshold, we found, first of all, unsurprisingly, that there was a very large increase in risk for accidental deaths. Again, this is not groundbreaking news or anything like that. This is the area where we have done a good job of capturing these risks over time, and we know it, kind of understand that part pretty well, probably. But we saw that on the day of the storm, there was a very high relative risk of 12. Showing this to some colleagues, they said they'd never seen relative risk this high. I had to agree. And then as you extend over the whole storm period, that goes up even more. But interestingly, when we look at some of these more general causes of death, we see some sign that there are increased risk there as well. And these are things that have been, I think, maybe less well characterized and where we might struggle more to capture it using those fatality tools. So for example, for cardiovascular deaths, we saw an increased risk on the day that the storm was closest to the county, and that increased some, although the uncertainty also increased, as we include days in the period around that. For wind speed, we also saw something for respiratory, although in this case, respiratory deaths are not that common. Accidental ones aren't either, but the signal there is very, very strong. So for the respiratory deaths, we saw kind of varying things when we looked at different metrics, and we always saw a lot of uncertainty. So that's an area where there could be something, but I'm not very confident in saying that we're seeing something quite as clear there. Suicide would be included, I believe, in the accidental. I think the coding goes in for that, but we didn't look at that specifically. There has been some really good research on mental health following hurricanes, and I think there are some studies there that have tried to capture that too, including, so here, remember here we're only looking up to a week after the storm, and some of those risks might come kind of well after that. All right. So we used an unconstrained distributed lag model in modeling this to try to capture the risk at different days of the storm. Here, lag 0 is the day that the storm was closest to that community. These are the lags after, which you'll often see in distributed lag models. In the case of hurricanes, we actually decided to use some of the lags prior as well and check out what was going there. And we did that based on a lot of anecdotal evidence that in the days before, people know the storm is coming and there are a lot of preparations, there are evacuations. A lot of people do much more physical effort than they normally would to try to prepare their home for the storm. And there's also potentially a lot of stress, which could serve as a trigger. So we found that the largest deaths for all-cause mortality were clearly, very clearly, on the day that the storm was closest to the community. But we also saw elevated risk from the day before to several days after the storm. And these patterns were similar for cardiovascular and accidental deaths. For respiratory, again, we had a lot of uncertainty in the estimates, and we didn't see much of a clear pattern there. Next, we looked at this using some of these different exposure metrics. So what I've been showing you so far has been this higher wind category. But for each of these, each color here is showing a different metric. So these are all distance These are rain. These are wind, and then flood and tornado. And then for those that are continuous, we explored several different thresholds for saying whether or not a county had been exposed to the storm. So for example, here, a county had to be exposed to 21 meters per second or higher wind speed for us to count it as exposed to the storm. So as you're moving down this way, you're picking up more and more county exposures to the storm. For wind speed, we saw, and this is showing all-cause mortality and then cardiovascular and the relative risk with the 95% confidence interval. We saw an increased risk at all of the different thresholds we considered, but in the case of all-cause mortality especially, we found that as we refined that more and more, we were getting higher and higher relative risk estimates. For rainfall, we saw an increased risk, but really only when we were using a very, very high threshold to identify the counties linked to that. And then for some of the other hazards that we looked at, we really didn't see much of an association between exposure to the storm and the risk. It's not surprising that these relative risk estimates are so different across these different ones, because I will remind you, these measure very different exposures based on the results that we saw when we looked at all the storms in all the counties and how well these agreed. All right, so to wrap up, I just want to talk about sharing the exposure assessments. So we collected all of that data, and we worked with our engineers, and we worked with our atmospheric scientists, and we tried our best to put together a very thoughtful version of that we think well captures the different risk. So we created that as an R package, and then we created another R package that links into it and can be used to query it. And so with that, you can do things like you can call a function and you can say, these are the counties that I care about. I want to identify all the storms above a certain rain limit, within a certain date range, a certain distance limit. And then for the rain, I want to sum up from the day before to the day after the storm came closest. So it's got a lot of flexibility in specifying exactly how you want to pick out the classifications for the storm. You can also do go for a storm, and you can look at the maps of rainfall for the whole storm and wind for the whole storm and all of that. And then this will return to you either maps or data sets that you can combine with time series data that have in each of the storms that you had, the date it was closest to that particular county, the distance the county was from the storm, the total precipitation. This also has wind, rain, flood, tornado events, all of the pieces that we were talking about before. Along the way, we also made some other stuff to make things easier for us, but we decided to put that out as software as well. So one of this was the storm wind model. I mentioned that we worked with some people who had some code for predicting electricity outages. So we worked to put that into an R package that we could use, and you can do it to gridded points, but you can also do it kind of to any plane of points that you want. This is an example showing, I believe these are the census tracts for New Orleans for Katrina. And so you can go in and at any of those resolutions, or if you have point data for specific people, you can model the wind speeds out to each of those locations using this. And actually, the engineers that we worked with went back and used the R package because we tried to make some refinements and work with some atmospheric scientists as we did that. And they used that this past fall to predict power outages for Irma. So, yeah. And it was actually a student who was an undergrad with me who's getting his medical degree here now who found one little bug in that kind of spurred them to change and try this one out. We also put in a county weather and county flood. So these go on top of some API access packages for USGS data, for stream gauges, and for NOAA NOAA rain. But these query and pull and aggregate to the county level. So they make it easier to take these kind of like locations of monitors and put the data together in a thoughtful way if you have county level data. We also did one that queries NOAA storm events and matches it up with the hurricanes and lets you explore some stuff with that. And finally, for the health data, we had it in local time. For a lot of weather data, it's in like Greenwich Mean Time. And so we did a package that if you have the county level, it can convert the time across zones. All right, so In our continuing work, one area we want to work on is improving the flood exposure metric. We have a few concerns. Mostly it looks like that's capturing what we want it to capture, but this is from a reported database. So there's the potential that it's missing some of the events and that it's missing them with a pattern. So in other words, a place that's more highly populated might be more likely, given the same storm, to record a flood compared to a place that's not. We also found the wind model for inland locations as the storm makes an extratropical transition. It doesn't do as well as it does right near the coast. A lot of these models were developed from planes flying, data that came from planes flying through and dropping sensors through the storm, and you can't do that over land. And a lot of the effort has been in trying to predict what the intensity of the storm will be when it makes landfall. So because of that, if we were trying to measure this for health, sometimes those models don't work quite as well. Also, with these health effects, we're noticing that if we take out like the 5 or 10 most notable storms, so Katrina and Hurricane Andrew in Miami, and a few of the ones like that, all of a sudden our estimates drop. So we're not seeing a whole lot. So it may be that the results that we're getting when we look at lots and lots of storms are really driven by these very severe ones, in which case one important question is, how do you pick out those ones that are going to be in that severe group? And then another important question is there much of a risk, an added risk, for storms once you get below a certain level? And then finally, we're looking at the effect modification of power outages, again, working with some engineers, and the impacts among Medicare beneficiaries for hospitalizations. So I'll just wrap up with putting my funding up and also all of the collaborators, as I mentioned, who have helped out with this. I think we've got 5 minutes for questions. Sorry if that went a little long.
I have a question.
Yeah.
So the excess, I guess, mortality that was kind of from the New York Times article, is there any idea of the different ways that you measured exposures? Are you explaining all of the excess mortality? Or is there a way to look at, like, you know, is there some other measure that isn't captured, or combinations of those measures that would capture it better?
Yeah. Well, we haven't applied this on that data. It would be interesting to try it out. And I haven't looked at each of these metrics specifically for Puerto Rico. I know that wind was a really big issue there, but I don't know if the other things like flooding were playing into the same degree. That being said, there are some pieces that were missing. And I think in that plot that I had of all of the different things, there's an arrow straight from the path of the storm to death that kind of is those things we might not know about. One of those, for storm surge, we're capturing coastal flooding with the flooding because those go into some of the storm events, but there might be some other storm surge that we're not necessarily capturing. And we didn't include that because that's something that only applies for coastal counties, and we were trying to look at measures that are further in. But that's one potential pathway. People have tried to take these different exposures sometimes and create a metric of kind of like danger. You can do that certainly with the software that we put out. You know, you could make that yourself. We didn't make one, and I kind of don't want to make one because I think it would be different depending on what you care about. And I think it's very easy to kind of try to make one all-purpose one, but depending on the pathways that you think are leading to a risk, I think that the influence of flooding versus rain versus wind versus all of these others could be really different depending on the different outcomes that you care about. So there are lots of different modeling tools now for trying to fit that for a specific metric, like a random forest type model might help with doing that and creating kind of the weights that you want to put on each of those exposures or the combinations or interactions that it might take in certain cases.
I wonder if that would distinguish the influence of the severe storms. If they're driving everything, maybe it's because they're high and all of those things.
Right. That is absolutely a question that is on my next to-do list, figuring out why for those really severe ones, is there something that you can kind of figure out as the storm's coming ashore, one of those characteristics that you can forecast or model that could help you pick out with some skill that this might be a really, really dangerous storm. Yeah.
I was just curious, you sort of looked at the time of the storm in terms of the immediate effects and storm period, does it matter what the length of that period is? I mean, if you modeled that, does that make a difference? I'm just thinking about, when the storm hangs on for days and days and days,
Yeah.
I could see things being worse, sort of in some kind of relationship. I don't know what it would be.
Yeah, okay.
Because at some point you run out of everything.
Well, there are a few pieces there. Some of these storms are very slow moving, and the actual forces of the storm itself hang around for a while. But we're pretty sure in almost every case we've captured that in the lag period that we've had. None of them kind of sit. With the exception, again, of the one tropical storm whose name has been retired, because it looped around and came back and hit the same area several days later. So that's, I think, the only one. We tried to look through where...
That didn't capture because of its weird, unusual...
Exactly, yeah. So you had like an exposure when it was closest, and then you had another exposure several days after that, and it wasn't that it was just sitting there the whole time, it was that it actually came back around, which is a fairly rare pattern. But there are definitely sustained problems where the disaster, the damage caused by those forces can have these lasting effects. Here, we were, as a first pass, trying to look at what happens immediately, but I certainly think that it's plausible, especially for very severe storms, and especially for some kinds of outcomes, like some of the respiratory outcomes that might follow from flooding, causing mold, and then some of the ones from mental health, things like that. You could get a very protracted risk. Yeah, I think that would be a really interesting question to try to look at going forward, and I think it's definitely possible. By comparing to other years, though, I think that I don't think that that's biasing our estimates of that immediate period. I think it's certainly the potential for longer lasting impacts. Yeah.
I think you answered my question about storm surge, but the other one I had is, have you thought about looking at socio-demographic factors? Because I guess I'm thinking, like, if you have a bad storm, you probably have a segment of the population that gets out of there, maybe isn't exposing themselves, but people who don't have that ability, this risk could be maybe a lot greater.
Yeah. That is another piece. I mean, again, like the next question is kind of what's causing what we see, and that is a really key piece. I don't have an immediate answer to your question other than yes, I think that's really interesting to look at. But I will note, there's a magazine called Significance Magazine that's put out by the National Statistical Association in England. I don't know if anybody's read it. It makes for a good read. It's fun if you're a nerd like me. But they did a little piece on, again, trying to estimate these excess deaths in Puerto Rico. And they looked at the period right before the storm and the period after. And first of all, they assumed that it was the same people there the whole time and did their estimates that way. But then they noted that like 100 or 200,000 people had left Puerto Rico for Florida after or right before because the damage was so severe. And so they redid their estimates for the number of excess by kind of bringing the population down that far. And again, they were doing their best at kind of, this is like back of the envelope ideas for what's going on there. But I think as soon as you start seeing those patterns, you absolutely have to ask the question, like the population isn't just down a certain percent from what it was before the storm. It's going to be very skewed across sociodemographics in terms of who has chosen to remove themselves from that area compared to the people who are still there. So I think that's a really important question for sure. Hard to answer, but conceptually a very important part of the process. Yeah.
Do you have a measure on disaster preparation for those issues? Because last Friday, the Dean's Lectureship invited Professor from New York University, Caroline, Gershon. She's specifically talking about this response issue.
Interesting, yeah. No, we haven't looked at that as a factor. That would go in with these different issues for why might some places have more severe or less severe impacts. One immediate way to look at that doesn't get all the way in but might take a first pass is a lot of these places are repeatedly hit. So someplace like Florida where you repeatedly get storms likely has gone through and done hardening of the buildings and at the community level more preparedness than someplace where it's very uncommon that it's hit. But yeah, these are all very interesting pieces for kind of the next step of trying to figure out what's going on. Yeah.
Well, we probably should go, but then let's give Brooke another round.
Thank you for having me.